So thanks very much to Amit and also to Rangarajan for asking me to give this talk here. I'm going to present something on this time series analysis for financial data. It may be a bit half-baked, so it's an ongoing process, ongoing project, and it's jointly done with the BTech engineering students from Pune, Saksham and Atharva. So they've been doing most of the computations. And the reason for me I'm traditionally a PDE man and work on models based on differential equations. So the idea is to get into more challenging stuff where there are no models. So that's why I got into time series. So I may be a bit ignorant, but just bear with me for this. So what's the motivation? So these two guys, BTech students, had earlier done a summer project in Pune, this astronomy center, where they looked at some astronomical data as a time series analysis. So they wanted to continue on those things, and in particular they proposed that they would like to do some machine learning techniques for time series. And the data we thought we'll look for is all India daily rainfall data, onion prices, stock prices, and astronomy. In this talk, I will be mostly concentrating on onion prices. Okay, so before that, I would like to first give you an introduction on neural network. What is it? First thing we must note is that it got revived from the 90s simply because of more data, huge data, and more powerful computers. So what's the motivation for this? Suppose you wanted to solve, let's say, a linear system like this. Then if A was a square matrix, you would just invert it and then get the solution. But if it was a rectangular matrix, M cross N, then we don't know how to get a solution for this. So what you do is you minimize the error. So this is the L2 norm, which is given by here. So if you try to minimize this in the least square sense, you would get a solution like this, A transpose A inverse of A transpose. Now note that A transpose A is a square matrix. And not only square matrix, it's symmetric and positive definite also. So, and how do you get this equation? By just equating the gradient of this guy equal to 0. Suppose in general you're given a function f of x, and then you want to approximate this guy by a linear combination of such functions where phi x's are given for a set of known this, then again you do a similar thing, except that you replace exactly this as this, but instead of this, you replace f of x minus capital F of x. Where this time the norm is the continuous norm, L2 norm. And now what is neural network? Neural network is exactly similar thing, except that you keep doing it for composite functions, compositions. So here what you want to do is you first, the definition is like this. You start with some value x, and then you keep iterating this. L runs from 2 to L. So here is L and L minus 1, so that means you know YL. Here, this L minus 1, sigma is a function, B is a vector, and WL is a matrix. Okay. It keeps changing. So this is the composition you keep repeating up to L times, and then what is that function sigma is that, and with the convention that it is component-wise like this. And what is backpropagation is exactly similar. Now we want to minimize this error here, y hat of I, which is compositions, observations. And then again you need to do exactly the gradient of j with respect to w, and then equate it exactly like this. So if you go back, it's a linear combination of functions. Instead of that, now you have compositions. You keep composing this. This is what they call learning. Okay, and so it's essentially least squares for composing the functions, compositions. So it makes it a bit painful if you look at this kind of matrix, and the derivative for this is given in this fashion. And similarly, you can do a matrix derivatives if you had a function like this. Suppose you had A transpose X, then the derivative is given in this fashion. And if it is a matrix, again, it is like this. If it is a square matrix and if it is a rectangular matrix. And now, in the case of the compositions, the neural network, it's a huge matrix and a pain to compute. So this is what neural network is all about. So the summary of these few slides is to tell you that learning deep neural networks is nothing but least squares approximations using compositions like this for sigma of this function, sigmoidal function. So of course you will ask immediately, how do you know this is going to work? Is there a theorem which says this? Yes, there is, by Sibenko. He did it in 89. So approximation by superpositions of a sigmoidal function. And here he says, forget about this definition, this is about this. If you had any continuous discriminant, the definition is given here, you need it in the higher proof. So the finite sums of this, CIN is class of all continuous functions defined on IN. And what is IN? IN is the tensor product of n times of interval I, which is 0, 1. And if you have, then you can find a function g which you can approximate it as closely as you please. This is just like Weierstrass approximation theorem, which says any continuous function is approximated by polynomials. So this is exactly similar for this function. So most of the time you keep hearing only I let my neural network learn, it takes a lot of time, etc. and all that. All that is nothing but implementation of this particular procedure. In the case of usual, if you did it for polynomials, you have Bernstein polynomials, explicit polynomials which give you the approximation. If you do with some other kind of manufactured basis and you do an approximate solution using L2 squares, it will be either finite element, least square, what you call Galerkian method. All those names are equivalent to this. So essentially, least squares with composition of functions is all about neural network. So what is the proposal here? The proposal here is the artificial neural network reconstructing the time series from the matrix containing its statistics. The only novelty here is you use the statistics to compute this. So in other words, you take a time series like this, and then you make a function sigma of y. What is sigma of y? Is all these statistics, mu, gamma, kappa, and so on up to st. And the proposal is exactly neural, as I already told you that it is a neural network. So find w and b such that this guy is minimized. Y is given to us. It is not y prime, it is L of wb. You find, and this is the usual L2 norm. Sigma is given, our usual 1 by 1 plus e to the minus x. And you find this weight matrix in B, given, remember sigma of y is a nonlinear function. It contains these statistics, which I'll just mention what they are, about 7 statistics. And these are all these means, skewness, kurtosis, variance, and all this stuff. About 8 of them are there. So what you do is you take the time series, put in these values of the statistics, and then we say that find a w and b such that this guy is minimized. So this is the recipe. Because you ask who gave you this, the standard answer is God whispered into my ears last night. Okay, so we don't know, it's just come up with this situation, and then inspired from all these stuff, that's it. Nothing, there's no big insight into this. Only thing is you must remember the sigma of y is a nonlinear function like this, and then this composition is there. Okay, so these are the statistics which we try to preserve, and the mean, all these things are well known, you know this, is defined. Now, first thing is to verification. So we use the Macky glass. So is this chaotic time series you can generate. So it was generated, and then we looked at it. And so again, let me go back and tell you what the method is. The method is you take an existing time series, find w and b, and then again for a new set of y, you calculate that. So x equal to this sigma of w of capital sigma of y, and then plus b. Sorry, plus b. Find w and b from the past data by using this technique. And then you get a new set of y's, plug it in, and get the new x. That's only the thing. So it seems to do a good job, at least in some cases. So for the Macky glass time series, it seems at least optically it's okay. And then we looked at some other things like ICICI Bank's stock price. Again, I've not zoomed in so that to really see how bad it is or etc. But overall, it looks okay. So we want to further refine this, of course. And here's another one, again over a short period. And of course, we haven't made any money so far, so by predicting this. And then we did the exchange, currency exchange. Let me tell you that people say that with all this sophisticated math, nobody has made enough money. The money made by Warren Buffett and all is using simple arithmetic. And so here's another US versus Australian dollar. And then similarly, Euro and US. And similarly, the Chinese yuan. So at least it is in the same ballpark, you can say that. So it hasn't gone off wildly. But of course, we're not too satisfied with this. This is again some return price of some test set which is available on the net. And so what was the conclusion of this study? So we use this whatever neural network technique which people call it machine learning. Deep learning is if the composition keeps going very big, it's called deep learning. Okay? So, and the proposed statistical features helped us draw some useful inferences, etc. And it was tested on all these currency, etc. And it was also tested, I have not presented this, on astronomical time series, which is what it says here. The forecasting of light curve performed modestly, but was unable to predict sudden fluctuations. The light curve is some astronomical quantity, light intensity of a celestial object or whatever, as a function of time. And so this is what came out of this study of some neural network / machine learning plus deep neural network with this. Now, this does not distinguish from any either lottery ticket numbers or rainfall data or the number of childbirth in particular hospital. So all are put in the same basket. So then we decided maybe there's something specific to financial time series. If there is anything, we should see that. So this is, in the literature they call it stylized facts. I think you must have heard of this. What are the financial time series characters? So what people usually say is that there is a long time scale which exists, or which is also called as long memory. So you must see that in all these physical phenomena, there's always small scale versus large scale, correct? In fluid mechanics, it's large eddy versus small eddy, then ODs versus this fluid mechanics equations. You have Boltzmann equation, which is at a micro level, and then Navier-Stokes, which is at the continuum level, etc. And similarly, small scale are traders and large scale are investors, because traders want to make money quickly. Investors are looking for long-term investment, correct? So the long scale effects are dictated by these investors. Small scale things are dictated by traders. So whether it's only the trading quantity which dictates this time series, or whether it is, so people feel that the long memory effects do exist. But how do you find that out in a time series? So it was started by Hurst. So this guy called Hurst, there's a Hurst exponent which goes in his name, and it was discovered by him in '51 while investigating the discharge of Nile River, and because he was trying to build that Aswan High Dam. So the behavior is essentially the tendency of wet years to cluster into multi-year wet periods, or dry years to cluster into multi-year drought periods. In finance also, the people found exactly similar. Huge changes are followed by huge changes, and small changes are followed by small changes. And Mandelbrot called it Joseph effect, simply because it came from some biblical region references. And there are a lot of these differences. Now, the following things I've flicked it from this article on Encyclopedia of Water by this guy, just to tell you what this. So all this is from that reference. So the possible explanation of the long-term persistence must be different from that of the short, of course. And however, its existence is easy to observe even in a time series plot. Now, what the Nile River data has data from 622 to 1284 AD for so many years. My God, this is really, even our Indian rainfall data is only there for 100 years, 120 years, because the British guys wanted to know. Why the British guys documented the Indian monsoon? Because they wanted to sail safely into the India from Britain. So otherwise, nobody cared monsoons. We only left it to the divine. So much data was there. And so there is a plot here, which I'll show you next. And what this says is, as you keep increasing the averages, there are still oscillations. So here it is. So here is what is plotted, the years and the nilometer index, whatever. So what is shown here is the annual, the orange ones are annual value, green is average over 5 years, and this is over 25 years, and so on. So what this, and here what is plotted is, we have to go back and read this. We can observe that the especially are much greater in the real world than in white noise. So even it beats the white noise thing. So the existence of fluctuation in a time series at large scale distinguishes from the random noise. So what we see is large time scale oscillations. So this is how Hurst discovered way back in 51. Or is this the same thing? Yeah. Okay. So now let's come to the basics. How do we, okay, we agree that there is a long-term effect and we need to quantify it and then calculate it from existing series. So that is what, and I'm a novice myself here, which is why I apologized to you in the beginning that I could be a bit vague here. So the following things is all flicked from this paper of long memory and self-similar process by this guy, which appeared in Toulouse Annals. So what is then the difference between the usual stationary process and long memory ones? So this is a question we would like to answer. Yeah. So the first thought that comes to mind is obviously about correlations. So suppose that xn is a stationary stochastic process with mean this and variance this, finite. But the corresponding, and let rho n be this correlation between x0 and x1. How does the correlation function as the usual stationary process behave? Of course, it requires some skill and knowledge to whether it decays to zero slower, polynomially or exponentially. So the most common ones all lead to exponentially fast decay. That means Gaussian type. A process with correlations that are decaying slower than exponentially fast is then unusual. So they are not even absolutely summable, then the term long memory is used. That means you have like 1 over x power alpha between 0 and 1. So that won't be integrable. So it will become infinity, especially from 0 to 1. So what he does is takes a very simple process, the autoregressive one process, and Zn's are identically independent distributed random variables with zero mean and non-zero finite variance, and then you choose a row between modulus of rho is less than 1, and this is the process. This is the most simplest process you can think of. And then if you choose the initial state according to this stationary, this can be written, this can be summed up, and then you can write it in this fashion. Okay. And then rho is, between mod rho is less than 1. So now you can rewrite it as, thank you. Yes. So now you can rewrite it in terms of negative index, and then these negative indians also exactly satisfy the same distribution, and so the entire, this product can be written up as a convolution, discrete sum, convolution sum of this. So here you see rho n is given by rho to the n, and it is exponentially fastly decaying. So this is the usual process. And notice also that the exponential becomes slower as rho approaches plus or minus 1, which we know that. We know that mod x to the power of n goes to 0 if mod x is strictly less than 1. Okay. And if it is minus or 1, then it cannot be made stationary. That is 2.1 here, if rho is plus or minus 1. So the entire process is already stationary. And notice that is again given by this, So in this sense, this is the usual process. Right. So then as we go to rho equal to 1, there is no real boundary layer between the usual stationary. This is again high school stuff in the sense that, whenever we wanted to integrate 0 to 1, 1 to the x power alpha, suddenly when alpha equal to 1, it becomes infinity. When alpha strictly less than 1, it is a finite quantity. So as it approaches 1, there is no some singular behavior or whatever. That's exactly what he's saying here, that there is no real boundary layer between the usual stationary process, which is decaying exponentially fast, and so on. So on the other hand, if it is -1, it will be a random walk. So here's a plot for rho. This rho is given here. This rho is this, and Zn is the white noise. And you have a random walk here, 0.99, 0.5, and 0. So overall, however, the class of this is too narrow to make to observe unusual stationary models that are being close to being non-stationary. So now we come to self-similar process. So self-similar processes are some such thing which you can scale it up. Okay. So a stochastic process YD is called self-similar with exponent h if for all this the y of c of t and have the same finite dimensional distributions. So usually in differential equations we make a similar approximation and write it down as a ODE from PDE to ODE when we expect similar solutions. That is exactly what happens if you want to look at, let us say, u is a function of x and t, and it satisfies du by dt equal to d square u by dx square, then you'll see that when psi equal to x by root t, then you can write this as a ODE. Okay, self-similar. So that means you want your solution u of xt to be equal to some v of psi. Single value. So that's exactly what is here, but except that there are no differential equations, there's only data here. Okay, so in applications, a self-similar is often modeled as a cumulative input of a system in steady state. So this is the usual abbreviation, and this is blah blah, I don't need to go into this. And some of the facts are presented below. So what you do is you look at this expectation of yt minus ys whole square, you manipulate it, and you'll get this expression. And you look at the covariance, you can further manipulate this and get into this expression. So if this guy is not 0, this has to be non-negative definite. It will be non-negative only if and only if this exponent h lies between 0 and 1. You can check this easily if it requires some algebraic manipulation, that's all. So in particular, if this h is called the Hurst exponent. So in particular, if h is less than or equal to 1, there's a unique zero mean Gaussian process whose covariance is consistent with self-similarity. Okay, so on. And the interesting and non-trivial models are obtained when h lies between 0 and 1, which is what we will assume. So in particular, you consider a fractional, I will forget about the, if you don't, I've not defined what this fractional Brownian, etc. and all this. But essentially, you will have this exponent in this fashion. And finally, this was also proposed by Mandelbrot, and Mandelbrot looked at Hurst's work, and then he came up with fractal processes, etc. and all that. So I will simply skip all this stuff, and then I'll come to the moral of all this stuff. So you calculate the Hurst exponent. How you calculate, again, I will not go into that because that will take a huge thing, a lot of. If you have Hurst exponent less than 0.5, it is short range, that means short memory. If it is 0.5, it is almost like a chaotic process. On the other hand, if it is bigger than 0.5, it has long range memory. So all this h is coming from by looking at it as a process like this. It is obtained by looking at this expression, correlation of this. So we want correlations which don't decay exponentially fast. Fat tiles with memory. Okay, so that is what this exponent measures. So of course you can do it on the Apple stock price, you can do it on Nifty index, etc. But I thought we should do it on our onion prices, Indian, because that is a complex system not yet explored. So I decided we will look at onion prices. So what's the reason for this? So India is the world's second largest producer of onions after China. So even though India consumes and produces a great deal of this stuff, its troubles out of eye watering price volatility is there. So in various major Indian cities, the prices have been quadrupled between May 2013 and October, before falling back at the beginning of the following year. A similar spike happened between this period. Well, the question is, why is this happening? Of course, we all know what, from everyday experience, we can say that a lot of people are coming in and lot of traders and more onion is being produced, exported. Government also wants to control the price. All these things are there. So, but nevertheless, let's see, just see. Okay, here's a picture, flicked it from this website. China is this much. Can you see that China is written or no? Yes, it's not clear, sorry. So this is China and this is India, that's good enough. Rest are all small players. So top producing thing is China and next is India. Okay, so Indian onion yield and area harvested. So if you see the year wise, and then you look at this is the yield per hectare, and this is the area cultivated. So the area cultivated is going up as of 2010, and it is still going up, I guess. And the yield is also going up quite dramatically. It's proportional, almost proportional to the. And what about the exports? The exports are also growing up. So you see from 2000 onwards, zoom, it's just people are exporting it like anything. And sorry. And what about imports? Imports are a bit oscillating. So the government is trying to do something there, manipulate or control. So in response to various price hikes and supply shortages, and given that the government severely restricts imports, it has favored increasing domestic supply through export controls. And these policies usually have mixed effectiveness. And it may be able to reduce the volatility by making greater investments in production and improving storage, etc. So of course, we all value the stable supply of onions. It permits very few imports from entire country, and trade in onions, especially import, is highly regulated. So even when the government foresees that weather will reduce the size of harvest, it tends to permit imports only after price starts to rise. So here it is again small scale manipulation, right? So you see the system is really complex. And the usual reason the government offers for restricting imports is that it wants to narrow its current account deficit. We don't know how much it's true that is. And the import of onion require government approval, etc. And when prices are high, these agencies are authorized to seek overseas suppliers to increase domestic supply. So this is the nonlinear interaction, I feel. Okay. And even if these companies manage to find these supplies, shipments have historically arrived too late to prevent a price spike. And the government frequently resorts to restricting exports in order to boost domestic supply and so on. It has raised the minimum export price a number of times over the last decade. Occasionally, these serve the function as these export bans, etc., and all this. So, in other words, what I'm trying to convey here is that the thing is quantified. The only quantification we have is the retail price and daily price. Rest of all are manipulating the system. The government, it's equivalent to stock price with NSE or whatever, RBI, etc. But then they are not caring about the poor man, whereas the government cares for the poor man. They want to make sure that the price, so that would be the difference between, let's say, a stock index and onion price. Onion price, if the stocks go up, everybody is happy, right? In fact, they will artificially also push it up. Whereas if onion price goes up, the government is going to fall. So they will make sure that the price comes down. So the system is slightly complicated than a financial system. So these interventions on distribution have had mixed effects, as they have been usually enacted too late to control these prices. So all this stuff, okay, fine. Now instead of what it might do, etc., what is the thing I want to say? Yeah, I don't think anything worthwhile is here in this, but we'll see the graph. Yeah, this is the most important. So what I plotted here is the days onion price per kg, and in different colors. This is data 1 is in the blue, the first one, and the next one is data 2, and data 3 is orange, and this one purple is the latest. And what are the periods? This is first one is July 98 to June 02. This is my own incompetence in getting this x-axis properly. Putting dates is a big pain. So this is 4-year period. So I've decided to take 4-year period. Okay, and so 98 to 2002, 2002 to 8, and so on. Okay, And so what is it that you see here? See, these guys in the olden days, at least it was not so bad. And then these spikes in these recent, in fact, this data is also not easily available. Also, data beyond this is not available. So even in this data, many times you see that date is given, but it says not applicable. Either if it is a missing data, you don't give anything, right? So why you give the date and then say that it is not applicable? So surely there's some manipulation going on there, right? So they don't want to put it down there, and you can't find data beyond 15. This up to 2015 is there, but not fully, only up to April or March. So that's why I didn't take that data. Similarly, some up to 97, from 97 December also it is there. So I just picked this for it. And then what I did was calculate this Hurst exponent. It's called the generalized Hurst exponent, and it is 0.49 for this, and so on. It has increased beyond 0.75, at least around 0.7, more than 0.75 in these cases. So that means from this quarter to this quarters, the long memory effects have come into play. Simply because I think a lot of exporters, importers, everybody is trying to make money and then trying to manipulate the system in some way or the other. See, the price has gone up to 60 now in this period, and yes. So this is what where this data come from? It came from data.gov.in. Got it from there. Of course, this site you can get it, but the cost is enormous. They want 80,000 rupees or some such thing. I mean, this place. What is this? Some growintelligence.com, GRO. So if you become a member, perhaps you can get the data. They have given some plot. I'll show you that. Okay, here is the plot from 13 to 16. This is from these guys. So I think the government has given to them, but not to us. So maybe they paid more money or whatever. So in fact, a mail was also sent to that. And of course, I'm sure the fellow who read that mail must have laughed away to death. Aha, this fellow wants data from 2015. Keep writing more and more. So this is from 2012 to 2016. Again, you can see that this keeps quite complicated behavior. But this curve looks so nice compared to this because this I plotted using MATLAB. So a lot of missing data and stuff. So I'm ashamed to show this. So I thought I will make up with this. And then we used our algorithm, whatever I was mentioning in the beginning. And that also seems to again agree with it. It's consistent with the previous data. I will not claim anything more than this. So what is it that we want to do? We want to incorporate these features into the proposed algorithm. That machine learning algorithm which I introduced in the beginning, it just took general statistics and nothing specific about the financial time series. So just 7 set of statistics, and we did a neural network, essentially a functional fit, nothing more than that. Neural network is nothing but a functional fit with compositions and with huge matrix derivatives. Correct. So this is here it is, right here. So you, as I wrote here, give past data of y, get the y, w and b, and predict new using this. This is all that is, nothing else. So it doesn't take into account any specific features of any financial series. So the idea is to now look at this onion data. Hopefully, if we get this data from either the government agency, or if we have enough money to buy this data, because after all the data is here. How did these guys get from 13 to 16? They have it almost up to 16. So if we can get from this, then we can study more and then predict. The Hurst index, the Hurst exponent is consistent with what is happening with reality. That is what. So I think I'll stop here. That's all I have to say. It's an ongoing work and it's half-baked, and I myself have not understood fully what this fractional Brownian motion, etc. Because I've been traditionally working in PDE and numerical analysis and modeling using physical laws, conservation of mass, momentum, energy, entropy, and things like this. Here we have nothing, right? So just you're given data and then say something about it. Thank you very much. Any questions? Okay, thank you.